Okay, now we're going to talk on the periodic chart as it relates to electron placement. Remember that we talked about the valence energy level. The valence energy level was essentially the energy level of the electron cloud that was the furthest out. There was a positive valence number, which is how many electrons are in the outer shell, and a negative how many to fill it. So, for example, if it's the second shell that needs 8, and let's say there were only 2 there, then the positive valence number would be 2, and the negative valence number would be 6. Okay. So when we go to the periodic chart is arranged in what we will call columns and rows. Columns and rows. When we look at a column, this is what we call a family. A family. And you know there are common characteristics in a family. When you go across a row, you're spanning a period. So family right here, period across here. So we go back. A row, a period, a column, a family. All right. Each row adds another energy level. So let's take hydrogen. Hydrogen has 1 electron to itself. So it would be placed in the first energy level. That is the first energy level. Helium has 2 electrons. So it too would be in the first energy level. Li, lithium, has 3. 2 in the first, 1 in the second row. Okay. We go further that everything in this column here would have 1 electron in the valence shell. So let's look at it. Hydrogen 1, lithium 2 in the first, 1 in the last, which would be the valence. Sodium has 11, 2 in the first, 8 in the second, 1 in the third. Potassium K has 19. 2 in the first, 8 in the second, that's 10, 8 in the third, that's 18, and 1 in the last shell. So you can see that here, and as we go this way, which is a row, what we basically are doing is each time adding an extra electron. Now, going back just to review, the number at the top here is the atomic number. That essentially is the number of protons. When you blow up the chart some, you'll see that the number down here at the bottom is the atomic mass using the atomic mass unit. Okay? So just to review. So we go, and here's another chart. So look at your textbook and use that to look at atomic mass, atomic number, then the symbol. Now we're looking at the combining atoms. There are basically 2 ways to combine chemicals, let's say, to make it in a simplistic way. One is to simply put them together physically. And that's what we call a mixture. If we chemically bond atoms together, putting a chemical bond we'll be talking about, that forms a molecule. So just to put chemicals together is a mixture, but to put them together with a chemical bond. Now, obviously, to put them together with a chemical bond requires quite a bit of criteria that we will be examining in the next few videos. Okay, but we start first with putting them together physically, a mixture. If you put them together physically in a mixture, they can be separated physically. If you put them together in a mixture and you separate them, all of the chemicals retain their original properties. So in a mixture, the chemicals retain their original properties, like dissolving salt or sugar in water. You could separate it. You could pour it through a strainer. All right. When you put them together in a molecule, it's like 2 people getting married, and all of a sudden they are a new team rather than 2 independents. And we'll be talking about that. All right. There are three basic types of mixtures: a solution, a sol gel, which is also called a colloid, and a suspension. The one that has the greatest criteria to put together is a solution. In a solution, it is homogeneous. What does that mean? Equally dispersed. That means if you had salt and water, and you had 8 amounts of water to 2 amounts of salt, no matter where you would pick a sample from, and no matter how big the sample was, when you boiled it down to its least common denominator, it would still be in the same ratio. So it's equally dispersed. Of the solution, of the mixtures, it has the most criteria because the solvent has to like the solute and vice versa. In there, as I mentioned, there's a solvent and a solute. I'm going to say it like this, not to be rhetorical. The solvent is the entity in the highest quantity. It's what's going to, it will be dissolved into. The solvent dissolves the solute. So the solute is in the smallest and the solute solvent is in the largest. Because what has to happen is the solvent has to form a complete shell around each solute particle. So that obviously means you need more solvent than solute. The particles of the solute must not only be attracted to the solvent, but they also must be small. You know that salt will dissolve in water, but if you took a great big block of salt and didn't chip it up, it would just fall to the bottom. So in a mixture, here's a solution, the solute must have some we'll say affinity for the solvent, and the solute must be in tiny particles in order to be dissolved. Okay? We go further. In a sol gel, which is kind of like Jell-O, it looks to be equally dispersed, but it's not quite. If you took it and you shined what we call polarized light, which is light that travels in one direction, you would be able to unmask the particulate particles. So in the sol gel or the colloid, it looks that way, but in fact is not quite equally dispersed. Now, why bring this up? There are many solutions in the body. All of our electrolytes, like our sodium, potassium, and so forth, are in solution in our fluids in the body. Why bring up sol gel? Because in the eye, we have something called the vitreous humor. So in various locations, we do have a sol gel type of particles. Okay. There's a colloid like milk, butterfat, and so forth. Again, I'm showing you the eye, which would show the vitreous humor, a jelly-like substance. Okay, a suspension is the least. Sand, if you put sand in water and stir it up and keep stirring it, it will stay suspended. So with a suspension, it doesn't really have to have any criteria. You just got to keep moving it. What's a good example of a suspension in the body? Our blood. Our blood cells, red blood cells and white blood cells, are only going to float as long as the blood is being pumped around the body. So when you remove blood from the body and you put it in a beaker or whatever, then the formed elements or the cells will fall to the bottom. So they are merely in a suspension. Okay? Again, study on this. Here's a solution. Here's a colloid. Here's a suspension. So you have plenty of material to look at with my PowerPoints and the textbook. Okay. When you are putting particles together chemically, you form a chemical bond. In order for chemicals or atoms to be combined chemically, there are several criteria that you have to satisfy. And when you form a molecule, which is to put atoms together chemically, we call it a molecule. If the two atoms are just alike, like carbon bonded to carbon, that's what we call a simple molecule. If the atoms are different, like in water, H2O, we call it a compound molecule. Okay, very simple. What are the main criteria atoms must have in order to form a chemical bond? The main thing that atoms want, that they desire, is to fill the outermost shell, to fill the valence shell. Therefore, if the valence shell is already filled, atoms will not reach out. So the reason an atom is reaching out primarily in order to bond to something else is to fill its outermost shell. Okay? Now, I'm going to go back, this is slide 51, to our periodic chart. Okay, in our periodic chart, from this little excerpt, these atoms here, let's say, are called the inerts. They already have a filled outer shell. Helium has 2 electrons in the first shell. Neon, 10. 2 in the first, 8 in the second. So the inerts have no reason usually to reach out and form a bond unless you destabilize them. Okay? So the main criteria is to fill that outermost shell. The main criteria is to fill that outermost shell. Okay? In addition to that, though, when you fill the outermost shell and the 2 atoms are more hooked together, they must be stable in 3-dimensional space because they've got to form a small geometric formation, and it must be stable. So in other words, for example, if there was $1 million hanging over a cliff and you saw it and you went to grab it but you fell over, then you got your first desire to have the million, but it's a moot point because you've fallen down the cliff. Okay? In order for atoms, as with anything, to hook together in a chemical bond, it involves certain energies. 2 energies are basically what we call electronegativity and, let's say, ionization energy. Okay? I'm not going to split hairs on the term electron affinity versus electronegativity. I'm going to lump them all into one. The difference, so to put it in a way, is this. Electronegativity, for our purposes, even though they're 2 different terms, but electronegativity in this biology course is going to say for an atom to hold on to the electrons it already has. Now listen to me, to hold on to the electrons it already has and reach out to get additional electrons to fill its outermost shell. So that's what our definition. Hold on to what you have and grab others to fill the outermost shell. So I'm going to pass on that. Okay, here's kind of my electronegativity chart that I put together in a way. Okay, now remember you're trying to, let's say, grab extra electrons. All right. The reason electrons hold to an atom is because they're negative, and in the nucleus you have protons. The electrons are flying around in almost the speed of light, but the reason they can't lose their trajectory and have to kind of go around like, let's say, the moon around the earth is because they're being pulled to the center by the protons. Now, imagine this. The more shells you have, the further the outermost electrons are. So they are not, it's harder for them to be held to the nucleus because they're so far out. So the next thing is, and we're going to put this together real quick. The next thing is that in actuality, I'm going to start right here with another video.